In this section of the proteins biochemistry notes, we're going to talk first about the amino acids, which is where we finished off yesterday. Those amino acids that are the monomers that make up the polymers that are proteins. We're going to talk about their structures. We're going to talk about how they then bond to form proteins. And then we'll talk about how we can analyze proteins by taking them apart. So starting out with amino acids and their physical properties, they're all crystalline. They have high melting points. They're more soluble in water than in nonpolar solvents, which must mean that they are polar themselves. And they're actually called Zwitter ions, and we're going to be talking about that on the next slide, what that word means. Amino acids are also amphoteric, which we talked about in the acid-base unit, and we'll talk about more in 2 slides. And amino acids also act as buffers in their chemical systems. And we have not talked about that yet. We could have in acids and bases, but it wasn't a requirement of IB in that section. So we're going to talk about that today in this section of biochemistry. So Zwitter ions, to start off, we said that they dissolve in water much better than in nonpolar substances. And since like dissolves like, we know that they must also be polar. Well, they're amino acids that are dipolar ions. And this is actually what happens in real life. We normally draw it out the way we did with the amine group and the carboxylic acid, but when we get that in our system, it naturally forms this Zwitter ion by having a positive and negative charge on one end. It's really an internal acid-base reaction. We know that acids are proton donors, so I have the carboxylic acid here donating its proton, aka a hydrogen ion, which is one proton. Once it's lost its one electron. So that one proton moves over to the amine group, and that amine group takes that, so that is a base. So the hydrogen from the carboxylic acid moves to the amine. This is an example using glycine, which is the most basic of all of the amino acids, because the R group here is just another hydrogen. So we see, again, carboxylic acid donating its hydrogen, so it's lost a proton, it's negatively charged, and that proton moved over to the nitrogen, so it is positively charged. I have a polar molecule. I have a positive side and a negative side, and that's what gives me this Zwitter ion. Again, this is what happens in natural systems, but we generally don't draw it out that way. We just draw it with the amine and the carboxylic acid because it's an easier function than drawing it out as this Zwitter ion form. I also said that amino acids are amphoteric, and thinking back to our acid and base unit, that means that they have properties and behave as both acids and bases. It depends on the pH of the aqueous solution that it's in. So that's going to have a factor on it, and we'll keep coming back to that throughout the rest of these notes today. As an acid, we know that acids donate protons, so when it acts as an acid, it's donating a proton. When it's acting as a base, it's accepting a proton because bases are proton acceptors. Again, a proton is just an H+ ion. An H+ ion, that hydrogen, has lost its one electron, so really all I have left is my nucleus with one proton, sometimes with a neutron as well, depending on which isotope it is. Here's the reaction. I've got my carboxylic acid that has donated its proton to the amine group, so this is my Zwitter ion. This is acting as an acid because this is going to donate the hydrogen from the amine group. So I have a hydrogen on its own here as a product, and then what's left over, it's not a Zwitter ion anymore because there's no positive and negative charge canceling each other out. I have this -1 charge on what had been the carboxylic acid left, but my amine group is actually an amine group again because it lost that one hydrogen. The base reaction for this, I start again with my Zwitter ion. It's going to take a hydrogen from something else in its surroundings, so whatever my aqueous solution is or my other whatever's in it. It's going to take that hydrogen, it's going to add it to where the carboxylic acid was. So now I have an overall positive ion, because I still have the positive from my amine group having taken that hydrogen initially, but now my carboxylic acid is there in full. Amino acids also act as buffers. Buffers are often natural systems. We see it going on all the time in the ocean. We see it in our blood, and these things help us out so much in so many different ways. They resist small changes in pH. So if I were to add more, let's say we start getting some acid rain in the ocean. Well, the carbonates that are dissolved within the ocean are going to react with that acid rain and basically neutralize it, get it back to the pH that it was originally. And that's what's happening within our bodies as well when we have systems in our bodies that are buffered because of these amino acids. This is really crucial to enzymes, which are extremely sensitive to pH changes. They don't work the way they're supposed to if they're not at the correct pH. We also can think about the isoelectric points of amino acids. It's the point where the amino acid is electrically neutral. So we're talking about the Zwitter ion here because it's got the positive end and the negative end, and so those cancel each other out to be neutral overall. If I change the pH that's around it, I'm going to make this Zwitter ion either acidic or basic, and that's using the equations that we saw 2 slides ago. The data booklet gives all of the isoelectric points that you need for any of the amino acids that it's going to be asking you about on the exam, so make sure to utilize your data booklet when you're working on paper 3. So we have an image here of the Zwitter ion in the middle. That's where we're starting with. It's at a neutral pH, so a pH of 7. If I have a lower pH than 7, so that means I'm becoming more acidic. Again, lower pH means I'm becoming more acidic. I've now gotten that extra hydrogen attached to my carboxylic acid. I have an overall positive charge. When I go in the opposite direction, so I'm getting a higher pH, so I'm in a basic solution, that's where my carboxylic acid is going to stay the negative, but my amine group that had been positive loses that extra hydrogen, so I have a no overall negative charge. So again, positive charge for low pH, 0 charge at neutral because the negative and the positive cancel each other out, and then at the higher pHs I have the overall negative charge. Okay, how do these amino acids form proteins? Well, they do it through condensation reactions, which means as I take 2 of them, they are going to lose a water. I'm going to lose an H2O each time I form a condensation. The bond is called a substituted amide, and the link, that bonding link, is often called a peptide bond. The 2 linked amino acids would be called a dipeptide. And if I start getting more than just 2 amino acids, which is what we have with proteins because they're polymers, I call them polypeptides. Poly for polymers, peptides because I have all of these peptide bonds. And there's still going to be an amine group on one end and a carboxylic acid on the other end, and that's how they're going to be allowed to continue reacting. This is my general reaction. So what's happening, I have my first amino acid here, a second amino acid there. It's the carboxylic acid, the alcohol within the carboxylic acid of one amino acid, and one of the hydrogens from the amine group that are going to be going off. So I have OH and one of these hydrogens go off. I've lost my water. All that's left here is an N and an H, and it goes straight to this carbon that's attached to the oxygen in the carboxylic acid. So I have my finished structure here. This is a dipeptide because it's formed from 2 amino acids, and that N that's circled there, that's my peptide bond, peptide bond right there. The protein structure, it ends up forming, once I get these long polymers in 3 dimensions, really complex, really interesting molecules that give us the vast array of processes and structures that these proteins can have and make us and the world around us so unique because of the way that they interact. So we have first and foremost the primary structure, and that's how the amino acids are connected, so the actual order of them. The secondary structure is any folding due to hydrogen bonding between the peptide groups. So we're looking at the the hydrogen bond between the carboxylic acid of one group and the amine group of the other. There's going to be interactions between those two, and that's forming the secondary structure. Now the R groups are also slightly affecting this. It's not what's actually involved in the hydrogen bonding, but it is going to have an effect, and then we're going to talk more about that in the next type of structures. There's two main types of secondary structures. We have alpha helixes and beta pleated sheets. So the alpha helix looks like this. This is a coiled configuration. That symbol right up there, that's just the Greek symbol. It's lowercase for alpha. We get a beautiful picture there. And all of the citations for the images are on the notes guide if you haven't noticed that yet. Then we have the beta pleated sheets. That is the Greek symbol for beta, lowercase b. It also looks a little bit like the German Sz. These are side-by-side polypeptides, and they kind of look to me a little bit like graphite. When we think of how those graphite molecules interact, it looks a bit like that to me. And again, we see the interactions between the carboxylic acid of one group and the amine group of the other. So the protein structure can then go to the tertiary structure. This is where those R groups really start playing an effect in how those secondary structures are really working. And we have hydrophobic interactions, hydrogen bonding, ionic bonding, and disulfide bridges. Finally, we have the quaternary structure that occurs when there is more than one polypeptide chain. So we can have like braiding of multi-alpha helixes as they are interacting with one another. If we have a protein and we want to know what's in it, the first thing that we have to do is break those peptide bonds, and we do that through the process of hydrolysis. So we're putting water back into the system so we can break those bonds apart, and those molecules are then stable enough to analyze. And once they're separated, we can either use chromatography, which we did with the TLC lab, or electrophoresis, which I'm sure you're going to do in IB Bio, to identify which amino acids are present.